All right, so now we're going to talk about the exact sequence of a pair, which is going to be useful. It's like basically a useful means of, amongst other things, computing relative homology. Okay. And then more generally, you'll illustrate it's like the power, it's like of long exact sequences. So, so these sequences are that exact. Sort of are sort of a convenient means of expressing sort of otherwise cumbersome relationships between homology groups. Okay. And in particular, what are called long exact sequences are extremely powerful. Okay. So a long exact sequence is a little bit like a chain complex, except that basically all the homology is trivial, right? So a long exact sequence Okay, and so in particular, it's like for the purposes of today's lecture, we're going to talk about the long exact sequence associated with a pair of spaces. And as I said, it's like it's going to be relevant in constructing or at least computing reduced homology. Okay, I'm sorry, it's like sort of relative homology. Okay, so before I state it's like the long exact sequence, it's like for a pair, let me at least give you some idea as to where this long exact sequence is coming from. So the sort of exact sequence for a pair, and what I mean is that I'm talking about K0, K, where K0 is a subcomplex of K, right, which is the usual setting for reduced homology, right, comes from the following sort of exact sequence, if you will. Okay, so the idea, if you will, is that if you look at the chain group on K0, right, there's a natural inclusion of this into the chain group it's like on K, right, because K0 can be included into K. So similarly, the chains it's like on K0 can be included into the chains on K. All right, and then from this, it's like there's a natural projection to sort of these relative chains, right? So K comma K0. And the thing to observe, of course, is that if you have something which starts in, as a chain in K0, it's included in K, and then it's projected, right? Then that's obviously going to go to the zero element in this relative chain group, because then again, it's something which starts, which is supported in K0, gets included into K, and then it gets projected into something where you quotient by CPK0, so this has to be, so something starting from here will end up in something which is trivial. Okay, so what ends up happening then is that you get an exact sequence like this. Okay, and we'll see it's like in a little bit that when you have sort of an exact sequence like this, there's a way to induce then a long exact sequence at the level of homology. Okay, and in any case, let me just sort of state the result first. And you'll see it's like this long exact sequence. It's like for the pair, and at least two of the three maps you'll see it's like are naturally induced. It's like by the inclusion. It's like in the projection maps. Okay, so and then the third one is this idea of what is called a connecting homomorphism, which requires a little bit more work to construct. Okay, so the exact sequence for a pair theorem is as follows, that so let K be a simplicial complex and then K0 is a subcomplex, then there is a long exact sequence which is as follows, that you take the homology group of K0, right? It's maps to the homology group on K, sort of via, again, a map which is induced. It's like by the chain map, which comes to inclusion, all right? And then this gets mapped to homology, the relative homology, right? So far everything is sort of fairly standard, okay? But the point is that then there is a map from this relative homology, it's like back into the homology group of one lower dimension of K0, okay? And then this is the part, this map is the one which is non-trivial, okay, and requires some thought to construct. Okay, all right. And the statement still holds. It's like if you have reduced homology groups, okay, so also holds when we consider sort of reduced homology instead, okay. All right. Okay, so again, it's like what we're going to see, it's like in a little bit, is that this particular long exact sequence is as a consequence, it's like of this sequence we have at the level of the chain groups, and then there's a general construction for constructing what is called the connecting homomorphism here. Okay, so let me say a little bit about what's going on. And then I'm going to show, it's like, more importantly, I'm going to show it's like how this exact sequence, it's like for the pair, gives you a very, very systematic way of constructing or computing, it's like the reduced homology. Okay? All right, so the map HPK0, it's like to HPK, right, as I said, is induced by this inclusion map. And let's just call it I, right, from CPK0 to CPK, right, which of course is induced by the inclusion, it's like of K0 into K, right, then the map HPK to HPK comma K0, right, is sort of is in some sense also induced by the inclusion. Okay, sort of what it does is that takes a p-cycle C in K, right, to the relative class generated by C plus CP K0, right? So this is again sort of the natural thing, right? This C plus CP K0, it's exactly what you would get if you're thinking of the map, the projection map from CPK to CPK comma K0 at the level of the chains, right? Okay, so again, these two are sort of fairly natural, right? This is again induced by the inclusion. It's like of the chain group on K0 into the chains into K, and then this map, the level of homology, is induced. It's like by this projection map from it's like chains. It's like on K to sort of these relative chains. It's like on K comma K0. Okay, so again, the part which is non-trivial is this map from HP K comma K0 to HP minus 1 K0, right? So the map HP K comma K0 to HP minus 1 K0 is what is referred to as the connecting homomorphism, right? Okay, and is sort of the non-trivial part, and is the critical part of the construction. Okay, all right. So I'm just going to erase this part here, just because we talked about that. It's like here. Okay. So, all right. So let's try to at least walk through. It's like how this is constructed, right? So you start with something. It's like which is in this relative homology group. So I want to. Let's say I let C, which is this sum of AI sigma I, right, be the generator of a relative p cycle, so which is an element in here, right? Okay, so what this means is that the boundary of this, right, is in CP minus 1 K0. Okay. So in K0, of course, the boundary of the boundary is trivial, right? So this implies that this boundary of C is also a cycle. And as a consequence of that, it represents a class in the lower homology group, right? So in HP minus 1, K0. Okay. So in essence, it's like this is sort of where the connecting homomorphism comes in, right? There's a sense in which this map here is induced. It's like by the boundary map, okay, acting on on this generators, and then so that's sort of the intuition. It's like, but of course, it's like these are at the level of homology groups, right? So you have to check basically that the map, it's like which is induced, it's like by this boundary operator is well defined. It's like at the level of these quotient spaces, okay, which basically means that the class, it's like which, okay, so if you start with a representative, it's like element here, take this boundary and then look at the class associated with it, right? That should be independent of the class should be independent of the choice of representative, right? So this is more or less, it's like the work, it's like which is involved is in showing that this map, it's like which I've expressed so far in terms of generators, is well defined and is independent of the choice of generators. Okay, and so that requires a little bit of work. And what happens again is that you're going to do this. It's like in a fairly general setting. It's like with some homological algebra machinery. It's like which we'll talk about in a little bit. Okay, so so how do we show this? Okay. So anyway, so the point is that this defines the connecting homomorphism. Because what it does is that it maps the relative class generated by okay, C plus CPK0, right? To the absolute homology. Class which is generated by a boundary of C. Okay. All right. So then, and again, it's like you need to check that this is independent of the choice of representative, right? So, so any cycle in the same relative class as C, right, can be written as C plus C prime plus C0, all right, where C prime is in sort of BPK, the boundaries, it's like, right, on K, and sort of C prime is in the set of chains on K0. Okay? All right. And this has to do, okay, so if you think about it, the reason why that's the case is because in some sense when you define it's like this relative homology group here, right, you do quotienting twice, right? Once is by quotienting cycles by boundaries, right, ZP, yeah? And so you have to add, it's like the flexibility to change the things which are in the boundaries, okay, and then it's, so the other one is by quotienting, it's like things in K0, so you have to add, it's like something which is in the chain group, it's like on K0. So that's sort of the general element, it's like in the same relative homology class, it's like in this, okay. So basically what that means is that you want to show that, well, if you start with C and you get to the boundary of C, right, you want to be able to add, it's like these two things here, and still say that the boundary of this whole thing, right, gives you the same element of homology. It's like on K0 as the original one, as the original C. Okay. All right, and why is that? Okay, so the first thing, of course, is that C prime is in the boundaries, right? So that means that the boundary of C prime is 0, right? So C prime is in the boundary, BPK. So this implies that boundary is C prime is 0. So that term doesn't contribute anything. So we're good. Okay. And the second thing is now it's a CP in K0. All right. Sorry, that's let's call that C. That's C0. I'm sorry, it's not C prime. And then we know that C0 is in CPK0, which means that the boundary of C0, right, is in is a boundary in K0. Okay, and that's okay as well because, right, HP minus 1 K0, right, is again a quotient group which comes from quotienting cycles by boundaries on K0. Okay, so so boundary C0, right, is going to map to 0. It's like when you quotient by boundaries on K0. Okay, so that is still okay, right? So the point is that the boundary of C plus C prime plus C0, right, is equal to the boundary of C plus boundary of C0, but the boundary of C0 is in the thing which you quotient by to construct this homology group, this absolute homology group, right? So which is sort of homologous to the boundary of C as a cycle in K0. Okay. All right. So anyway, so that basically is a proof, right, that this connecting homomorphism, which is induced by the boundary map, right, and is actually sort of well defined on this map. It's like from relative homology, it's like to absolute homology of one dimension lower. Okay. Okay. So with that in mind, now let's just try to use this. It's like to construct some relative homology groups, okay, or to compute some relative homology groups. So let me just restate the exact sequence we have, and then apply it to a calculation. So again, let me just rewrite this. So the exact sequence of a pair, right? So you have K, a simplicial complex, K0 contained in K is a subcomplex, and then we have a long exact sequence which goes from homology of K0 to homology on K to the relative homology on K comma K0. And as I said, this part of the long exact sequence is induced by the inclusion and then the projection maps. Okay, and then the last part here is this connecting homomorphism, which is in some sense induced by the boundary map. Then it sort of repeats. Okay, so let's look at an example. Okay, so let's consider the pair sort of the three-dimensional ball quotiented by its equator. So So the sort of tree ball modulo the equator. Okay, and then let's say it's triangulated, right? So I want to use this exact sequence to compute the reduced homology of this pair. Okay, so the relative homology of the pair. Sorry. So if I use using reduced homology, right? All groups of the ball are trivial. Okay, and in fact, of course, if you recall, it's like that's the reason why we introduced the idea of reduced homology. It's just so that things which are contractible, it's like have trivial reduced homology, right? And then so similarly, it's like with respect to reduced homology, right? The only non-zero sort of reduced homology group of S1, right, is the first one, which has rank 1. Okay, so what that means is that except for dimension 2, so we're going to apply it's like this exact sequence of the pair, and B3 is going to correspond to K, right, and S1 is going to correspond to K0, right, once you've appropriately triangulated everything. Okay, so right. So the point is that most of these things are going to be 0. It's like except for basically the dimension p equals to 2, right? Because this is saying that P1 of S1, right, is non-trivial. Okay. So sorry. Okay, so this is saying, let me just say it, right? So H1 of K0 is equal to Z. Let's just say Z2. Okay. And then everything else is non-zero. So basically, again, except for, and again, it's like this is the one which corresponds to HP minus 1, so that means P is equal to 2, it's like in this case, right? So except for the P equals to 2 case, right, everything else is 0. What happens is that HP K comma K0, right, just looks like that. Okay, so that's an exact sequence, which implies that this thing itself has to be 0. This is exact. Okay, so this implies that HP K comma K0 is equal to 0 for, again, P not equal to 2. Okay, so the P equals to 2 case, right? So the P equals to 2 case looks like the following. You get 0 maps to H2 K comma K0, right? Well, let me just, actually, I'll write it just in terms of the B's and S. So B3 and S1. Okay. All right, and then here it's like, again, is this connecting homomorphism. And because this is to H1, this is the reduced homology, right, which I denote by a tilde. It's like on S1, then it maps to 0. Okay, So again, this has to be exact, right? So, so this map here, so in order for this to be exact, this map here has to be both injective and surjective, right? So by exactness, right, the map from H2 B3 S1 to the relative sort of reduced homology, it's like on S1, right, is both injective and surjective. So that means that this thing is isomorphic to this sort of relative homology. It's like on S1, right? Sorry, reduced homology on S1. Okay, so H2 B3 S1 is isomorphic to the reduced homology of dimension 1 on S1. Okay, so that means this has rank 1. Okay, all right. So yeah, so again, that's an example of how you can sort of exploit sort of long exact sequences, in particular long exact sequence for a pair, right, with knowledge of the homology, either the reduced homology or the regular homology. It's like of the spaces K and K0 to then compute the relative homology of the pair K comma K0. Okay, so and again, it's like what we're going to do. It's like in the next couple of lectures is to then sort of talk more generally about where this connecting homomorphism comes from. Okay, so let me just stop here for now.